Yeah, so hello everyone. So I'm going to be talking about what we did with Postgres and our company. So a little bit about me. So I'm Rohit. I've been I'm a senior software engineer at Radastat. I've been with Radastat for the past 5 years, and I've been working with the Postgres for the last 7 years. So Radastat, so we work on the real-time data platforms, and yeah, I graduated from IIT Madras. Explain a bit about what Radastat does. So Radastat is a data collection tool. So we help customers collect their data of their customers from, be it your Android app or iOS app or whatever, and we deliver them to destinations. So we are a real-time data delivery tool. And when you hear of real-time data delivery, the general consensus or the typical workloads which we use are like, say, a queuing system like Kafka, Pulsar, or RabbitMQ or whatever. But we chose to use Postgres as our queuing system, and we have been using it for the past 6 years. And we've been working with a lot of heavy Fortune 50 customers, and it's been working very well. So now, a couple of reasons why we chose Postgres over Kafka. So we are a multi-tenant system. So in a multi-tenant system, we serve multiple customers, and each customer has different data sources, and it is connected to different data destinations. So think of it like the data pipeline where you connect your source to a destination, and we have multiple of such source destination combinations, and we want to isolate performance of one pipeline to another. Now, since we have a lot of customers, we would end up with millions of such data pipelines. And on a system like Kafka or Pulsar, we would have to have a topic for each of those data pipelines, and some data pipelines would have a lot of traffic, some data pipelines would have no traffic. So not all the workloads are same, and this would result us with a heavy maintenance overhead when we use such a queuing system. But with Postgres, what we ended up doing was we realized that we can have virtual queues on top of tables by making use of indexes and partitioning the data in the right way, having the schemas, and we could also change the way we get data. Instead of a direct subscription from a queue, we could change our query patterns on runtime, and we didn't need to do any data migration and just needed to add indexes to improve performance and whatever. So we chose Postgres for some of those reasons. Now, I'll just explain a bit about how we organize the data in our queuing systems. So every event or every event we receive, I would say it as an event or a job. So both of them should be synonymous. And for every event, we should have a status. So an event can be delivered to a system, or we could have failed deliver into the system, or whatever could be the case. So whenever we get an event or whenever we ingest an event, we write it to a table called jobs table. And for every job in the jobs table, we'll have an associated status table. And the status table is an append-only table. So whenever we try attempting to deliver the job, we whatever the status we get, whether it was successful or failure or whatever, we just append the status in our status table. And based on our pipeline ID, which would be the source destination pipeline combination, we would want to provide some isolations and guarantees. So this is how the data is organized. And also we have ensured that every data set would not have more than 100K jobs. So why did we do that? Why did we not have a single monolithic table and we ended up having such smaller 100K data? Is because we realized that when you have smaller tables, and querying on top of the tables is much faster than having a very large table, because all of this data could be fit in Postgres RAM, and it could serve the results from in memory than doing the disk reach. So instead of having the very large table, we ended up having some smaller tables, and we have a lot of such tables. So this is how we organize the data. Now, in the initial days when we started out 5 years ago, everything looked fine. We didn't need any index, and we were able to achieve our performances. And yeah, one more thing which I want to mention here is that when I mentioned real-time delivery, we want to deliver the data within, say, 5 to 6 seconds. And we want to do all of that with Postgres. So we want our queries to be really optimized, and we cannot afford queries going into seconds, and we expect the results to be, Postgres query results to be in milliseconds. So when we started out, we didn't have much of indexes, but as we started growing, we realized that the query patterns were becoming heavier and we were not able to meet the latency requirements. So we started analyzing our data. We started analyzing all the queries which we were getting on Postgres. So we took dumps of the PG stat activities over the course of the day. We looked at what are the main queries, what was taking time, what was not taking time, and at what points of days were we having data which was taking time. So then we realized that we were fetching data which was not processed or not delivered, and that was the only data we needed to, only query we needed to deliver the data. So when we did that, we realized that we need an index on job ID and job state. So job state could be either success or failure or whatever. And to come up with the indexes and to see the effectiveness of the indexes, we used an explain analyze statement on every query which we rewrote. And we couldn't have too many indexes again because we are a write heavy system. We keep getting data real time and we have to take care of both ingestion, querying, reading and delivering. So we could not have too many indexes, and we also have to balance. And as you know, with adding each index, your write performance would go bad because you have to add the data to the disk, and you'd also have to add the data to the indexes. So our write latencies and read latencies, we have to balance both of them. So every index we add it very carefully or cautiously. Now as I mentioned, like we have millions of pipelines and we have one table or few tables. Now each of these tables, there is only a certain number of pipelines which are active at any point in time. So how do we identify what are the pipelines which are active? So if you are aware of how MySQL does or some other new age databases like Hyderabad does, they have this index only scans or loose index scan which we call, where you can query data on indexes and get the results. So you don't actually read the data in the table, but rather read the data from the indexes. That is not natively available in Postgres. So, but we wanted the active pipelines which have data at any point in time. We wanted those results. So what we ended up doing was we used a recursive query on which does only index only scan. So how does it work? So I know that I have a lot of data, but only a smaller number of pipelines. So I know that at any point in time, I don't have say more than 30 or 40 pipelines which are active. So what I did was I did something. So this query translates to something like I get the pipeline ID which is the highest. Then I do a query which says that get me one pipeline ID which is lower than this. So, and I do this one by one. So this would ensure that we only get the pipeline ID, one pipeline ID at any point in time, and it does index query. So we don't read all the data in the table, and this was much faster. So we were able to get all the unique pipeline IDs within say milliseconds, and this proved that okay, we were able to do this on runtime and we were able to optimize things a lot. Yeah, now the next problem was that say we have to deliver data to a data warehouse or a Postgres data table, and the Postgres database is undergoing some downtime. So whenever we try to retry those data, you would end up with a large table bloat. So we just keep appending failure, and within minutes, and since we are a real-time delivery, say that every 5 seconds we try to attempt 100k jobs. Within say 1 minute, you would end up with a 2 million or a 3 million table bloat. And as and when our status table grows, whenever we try to do a join and get the latest or the pending jobs, we have to do a large join, and this ended up making our queries much slower. So what we ended up doing was that there were two things which we did. One thing was that we only wanted the latest state of any job. So we did periodic compactions on the status table, where we realized that where we ended up deleting the data, and we didn't delete the data. We moved the table, we copied the latest entries by using the rank query and moved the latest entries into a new table. So this is something we did. And after every mass insertion or mass movement, we had to do a vacuum analyze to reclaim the space. So why did we need to do vacuum analyze was that the Postgres stats were getting messed up whenever we did such large operations. So it doesn't get the time to update those stats in its, and the query planner was using the wrong query, which was in turn bloating our query times. So after doing such large operations, and since we were doing time over time, we had to do a vacuum analyze after every step, because this would help Postgres reset its queries, because it does read the table at that point, and the query planner was able to take the right decisions. Yeah, so, and whenever we have a table or a 100K set of data which was fully processed, we ended up dropping the table. We had no use of that data, we were completely delivering it, so we ended up dropping the table. Now, if we had multiple smaller tables, where each table had, let's say, 10 jobs or 20 jobs pending, having multiple such smaller tables was also not something which was helping us with query performance, because each table contained metadata associated with it and some stats associated with it. So the amount of data which Postgres could hold in its memory was getting reduced, and we had to go to disk operations and read from the disk. So what we ended up doing was that whenever we had smaller such data sets, we ended up merging all of them into one such table, so that Postgres was able to reclaim some space. So, and whenever we did all of these operations, we were also, whenever we did all these maintenance operations, we also ensured that we didn't have any pause during processing, and we were able to process the data as and when we can. And on top of this, we did some more optimizations. So whenever there's a data set which we query for a particular pipeline in a data set, and if this pipeline data does not exist in the data set, we put something in our in-memory cache saying that, okay, instead of querying it again, we return the result directly from the cache saying that you need not query this data set, because it does not have the data with respect to this pipeline ID. And also it was the same with the active pipelines. On a data set, once queried, we know that what are all the active pipelines which we had in that data set. So we put all of them in memory and were reusing it. So doing such smart optimizations helped us reduce the load on the Postgres, and the number of QPS which we did was reducing drastically, and we were able to extract more and more and do other operations instead of doing the same operations over time and time again. And apart from this, we also had to tweak some of the Postgres configurations. So one of the major challenges we have is that since we are a real-time ingestion queue or whatever, we could not afford Postgres downtime. So Postgres, whenever it goes down and it tries to thumb up, it has to checkpoint all the data which it couldn't write to disk from the val. So this time could be very long, and if our Postgres doesn't thumb up within, say, 1 minute, all the 1 minute we were not ingesting data. So we had to change the checkpoint settings, the worth mem and everything, so that we ended up checkpointing as fast as we can, so that whenever the restarts were much faster. And after doing all this, we also realized that the bottleneck now was at an IOPS level, so we were getting throttled on the disk and on the number of and an IOPS and the bandwidth level. So we also ensured that, okay, we had alerts and checks on them, and we were able to act on them. And yeah, so the performance again is not something one time. So as and when our workload changes, as and when things change, we end up having new challenges. So we have a performance benchmark per se, which we built on our own. So it's an open source code base, and all of this framework is open source. So we have even this benchmark open sourced on how much performance can we get from a single Postgres container, and how many writes, or how many MBs write and how many MBs can be read. So yeah, and we continuously run it to see if there are any new performance bottlenecks which we are having by the changes which we made over time. And yeah, so this is how we are keeping track of the performance which we can extract from this. And yeah, right now we are doing about 1 billion events per day or something of that sort in both ingestion and delivery, and we are able to achieve like sub 10-second delivery. So we are we are able to do things which people assume that only something like Kafka or Pulsar does, but we do this with Postgres. Yeah, I think that's all I had. If anyone has any questions, comments.
If you look at the checkpointing piece, can you go to the earlier slide?
Yeah.
So compare the caching strategy and then the memory optimization here versus the checkpointing you are doing. How are you balancing the memory footprint? What are the configuration, the systems that you are working on where the Postgres is hosted?
So we shard the Postgres into multiple smaller Postgreses, and each Postgres is very like a very small thing. So we use like 3 CPU and 4 GB or 6 GB of memory, and the data is sharded across multiple Postgreses. And I think that we have it in a blog, the configurations which we are running. I can just share the. I mean, we did a lot of experiments. So, and we came up with some sort of checkpoint numbers, and the reason why we did that. So we brought down the checkpoint from 5 minutes to 30 seconds so that we could flush it faster. We increased the worth mem, we increased the hash mem multiplier. So we increased the maintenance worth mem and stuff like that. So is this what you are looking at, or?
Yes.
So yeah, after all these experiments, we also realized that we had to change some of the Postgres internals to suit our workload. So this is what the numbers we came up with for the performance which we wanted. So this random page first is something which would help Postgres choose indexes over sequential scans. So sometimes Postgres tends to choose sequential scans when it feels that index scan is much worse. So we wanted index scan for the most of the cases, so we reduced the random page cost. And we also wanted auto vacuum to be happening that much frequently, because we end up adding data, removing data, deleting, dropping data sets, and this results in a lot of unclaimed spaces and a lot of tuples which are not cleaned up. So we want auto vacuum to happen, or else it would just bloat things up. I haven't added all this because this was hard to put in one slide, but we do have a blog which has much detailed explanation of whatever he did.
And the references slide where you will push all of
Yeah, I'll just add a blog.
That is good for the audience.
Yeah, sure.
How did you manage the data sharding?
So basically, it's not data sharding that like the traditional way. So for any system which we have, we route the data into multiple different Postgres pods based on some identifier. So we just route it into different pods, and each of them is its own owner. Like it does not care about the other thing.
There's no leader coordinator.
No.
mechanism.
No, so that we tried doing that, but for the scale which we were doing, that would prove to be costly. Like having one write would again, one writer or multiple followers would lead to latencies of copy.
I'm not necessarily asking about one writer and
Okay.
multiple readers per se. If we look at a query which is trying to aggregate from multiple shards, is that even a viable
No,
use case for
it's not a use case for us. So yeah, so we receive data and we need to deliver it. So our use case is we need to deliver data for a user in order, and each user's data we know that resides in one shard. So or we would break it into two shards, but it would be like you wouldn't. There's some unique identifier, and each unique identifier would always end up going to the same shard. So we don't need to aggregate across multiple shards, but sometimes we need to increase shards or reduce shards. We have built a separate utility for that where we could move data around, in and around.
Awesome.
How large is the cluster? I think if I were running the Postgres pods in given
Yeah.
so I'm using any cloud or else,
No, we run the plain Postgres images.
Okay, is it a managed cluster or are you guys
No, we manage on our.
you manage your own cluster? And how large is it? I mean, like, because I could see that it's around 100K even in a second, right? So,
Yeah, so if you're talking about the number of Postgres pods, we run around 800, 900 Postgres pods. Yeah. So it's a pretty large cluster.
yeah, yes, exactly.
Yeah. But yeah,
Have you guys thought about comparison of the cost versus Apache Kafka versus a Postgres was running in Kubernetes setup? Because I understand that you guys have built a layer on top of it to optimize all the things for running. We previously looked in Apache Kafka. Did you compare these two cost analysis?
So,
That's
yeah.
the cost I'm talking about. Of course, the software is paying off and the changes which you made. Yeah.
So it's also not just about the cost, it's also about the business use case or what we want to achieve from the thing. So I would say that okay, 4 years back the business use case didn't make sense because the kind of features Apache Kafka provided back then did not suit with the business requirements we had and the isolation guarantees we had. Now it sort of Kafka picked up a lot and now it sort of made sense. So yeah, we are looking into that. But again, so managing the Kafka cluster is not as easy as managing the Postgres cluster. So there's also a maintenance overhead which is associated with that. And if you go with a managed MSK or something like the Kinesis or whatever, that turns out to be way costly than just running. 800 pods with 2 CPUs is around $1,600, which is much cheaper. But for a Kafka of similar scale, you might end up blowing that in 1 hour or so. So yeah, we are still experimenting with a self-managed Kafka cluster, but I don't think we can replace Postgres. It would be something like, it's a system which was built over 5 years. So it's not that easy to completely rip and replace every function. This is just like one of the few use cases which we use, but our system is completely based on Postgres. We use replication, subscriptions, and we heavily rely on transactions to ensure that then we show how many events someone has sent, how many succeeded, how many failed. And in a system like Kafka, to know that exact number is very hard because you don't have the concept of transactions. So transactions is something which we heavily use, and that is one thing which is stopping us from completely migrating. So we can experiment it, like Kafka has grown a lot, we acknowledge that, but yeah.
Of managing the Kafka versus the cluster.
A managed Kafka is much costlier even in this day than a self-managed Postgres, but a self-managed Kafka is something which we have to see. A managed Kafka or a managed Pulsar is something we are exploring, but yeah.
What are you using for replication? Rep manager or?
No, we not replication. It's publish subscribe. So we have all of these shards which publish an information.
Right.
We have a central Postgres which subscribes from there, and we have an API layer on top of that so that we can show up some information. It's the Postgres native publish subscribe.
And using the CG output plugin.
Yeah, the normal logical replication which Postgres provides.
output
Yeah,
plugin.
yeah.
Thank you, Rohit.
Thank you.